Alright, so I got sent an interesting video. Uh, Basically, the essence of the video is this. You have something like an ankle grinder, and you have a disc, and this disc, for whatever reason, isn't attached properly. It's spinning around really, really quickly, point of an ankle grinder, and it gets shot off into a room. It bounces around for a bit. It takes a path which goes something, so where the video begins, it like hits a table or something here, bounces off of that, then manages to turn itself around, then goes off in another direction, bounces off of something, and then hits a corner and kind of falls over. The video cuts. But there's some interesting stuff going on here. So this all in and of itself kind of fine. If the spinning wheel is spinning like this, hits here, bounces off, okay, this all makes sense. It turning itself around, well, that's fine, right? Because we've got, as it spins around, it's exerting a frictional force on the ground, pushing the ground that way, and the ground is exerting a frictional force back, pushing the disc that way, Newton 3. Therefore, like, it turning itself around does make sense. So that's kind of fine. I didn't see within the video an instant where it turns itself this way around without it having hit something. So that all kind of makes sense, but there was one bit which, basically the question was, is this video real? And there was one bit which seemed really, really weird to me, and it was the fact that I basically drew its path along the ground a second ago, but that wasn't all it did, because it also spent a lot of time bouncing into the air, because, I mean, obviously, it shot off from something, it's falling down, so you would expect it to bounce a little bit, but there's an interesting question as to how it should bounce, and more importantly, is it fake? And the reason why the question is it fake, is because at some point, the disc manages to bounce itself upwards. Now, just to clarify for a second why that is so weird. If I've got a disc spinning at any speed here, let's just say the disc is perfectly, like, it can't perfectly be, in this, the disc is definitely spinning too fast for it to be rolling. But let's say that the disc is bouncing with, like, a pretty small height above the surface. So, say here. How is the ball going to get up here? Or not the ball, the disc going to get up here? In order to get up there, it needs to have some force exerted to get it up there. It has some change of energy, and that change of energy has to be applied. There needs to be a force that gives it that change of energy, and that force must be pushing upwards. But what force do we have in our system that can do that? This is, like, not obvious and not particularly clear. What do we have that can manage to push this upwards? It definitely does in the video, and I'm confident myself now that the video isn't fake once I came off and answered this, but it's a difficult question. It's not something I instantly saw the answer to, because if we, like, take a look, imagine the instant it's hitting the ground. Whilst it's in the air, there are no forces acting on it, so it can't be whilst it's in the air that we're doing anything interesting. So we take the instant when it's hitting the ground. What are the forces? Well, there are a couple of forces. There's the, so if we're talking forces on the bowl, there are two forces acting on the bowl. So it's spinning like this. One of them is the normal reaction force, and the other is friction from this surface. So we consider the relative velocities at this surface, and you can see friction will end up going this way. But this is weird, because the normal reaction force is conservative. Or at best, it's conservative. Okay, I should say we're not precisely dealing with the normal reaction force, because there also is the potential for some energy loss, but the point is the normal reaction force is the only force pointing upwards. But what the normal reaction force does is it balances the weight that's coming down. So there's no way you can ever have something under just that force which ends up bouncing up higher. Or so it seems. Definitely, this force cannot on its own bounces up higher. And so basically, if this video is to be real, which I claim it is, then something in the model is screwed up. And as a physicist, I was very confused, because of course I only ever deal with perfect things. I was beginning to think, what if something was slightly less perfect? And then the person who sent it, who is an engineer, was like, what if imperfections, or does engineering-y stuff. I don't know exactly what he does, but he seems scarily competent as like mechanical stuff. It's scary. I'm a physicist. I don't like the real world. So here is the simplest model, and okay, this model isn't accurate, but we can build a more accurate model off of this. And so here is the simplest model we can come up with, or I came up with. Here was the first one. So we imagine a ball, the disc, doesn't matter, it could be a ball. I'm in 2D, they're identical. Disc comes down like this, and it hits here. Now, the trick is, okay, the first way we can see a bounce happening is, let's imagine the collision is actually perfectly inelastic, i.e. the ball hits here and actually just sticks, basically. It just remains along here. Well, when it does, it's got a ton of velocity this way, and so like, that's huge. And so there is going to constantly be a frictional force. This velocity will be here for like a long period of time. So there's going to be a huge force, which is just going to build. And whilst it's in this place of positive curvature, that's just going to keep building. And then eventually it shoots itself off up here. So you're going to have a roughly constant frictional force throughout here, but it's there for some finite period of time, therefore it bounces up. And we can kind of see that maybe something like this might make sense. One hint that we have is the fact that this ball is bouncing around a huge amount. It maintains being upright for a good, like, minute or so in this video. Despite the fact that it's making friction for contact, despite the fact that sparks are literally flying off of it, this thing is rotating incredibly quickly. And therefore, like, by default, if we had, like, direct transfer of this rotational motion into upwards motion, or direct transfer of, more accurately, the rotational energy into gravitational potential energy, it should be shooting way up past the ceiling. Like, there's no way that disc is still in the building. So we know that's not what's happening. We know there's no direct conversion of energies. And so, or there's no, like, complete conversion of energies. Whatever this process is necessarily has to be incredibly inefficient. And so what we can do is we can begin to visualize what sort of processes were. So came off a rough one there. That one's not brilliant, but we can go one better. That previous process basically worked off the idea that we made contact and we remained in contact. But that's really unrealistic. We know that this thing is bouncing up and down a lot. It's bouncing up and down very frequently. But it's keeping going for ages. That suggests that it's spending very, very, very little time actually in contact with the ground. So a better model might be something like this. So we start off with disc here, disc falls, disc bounces off of here. But there is a tiny amount of time where this is in contact. And this is the amount of time, whilst it's in contact for this period of time, we're going to have a couple of things happening. Firstly, we're going to have some gravitational force going down. We're basically going to, if this weren't spinning, we'd just get a simple bounce off of here. Right angle, bounces off, goes here. But that's not what we have. Here we also have some force here, which is going to produce an additional frictional force. That frictional force is going to be pointing downwards. Or it's going to be pointing parallel to this. Now, the interesting thing with this, of course, is that this, the change in momentum, we have F equals dp by d. For some reason, physicists call momentum p. I don't know. It's historical. Don't ask too many questions. And if I want to work out the change in energy we're getting out of something, well, the way I'm going to... Sorry, I'm talking nonsense. If I want to work out the change in momentum we're getting, I can just approximate that fairly quickly by just saying the length of time multiplied by the force is equal to the change in momentum. If we do that, well, it's bouncing off incredibly quickly. In fact, high coefficient of restitution bounces, which is what it seems like we have here, they're actually, like, there you're going to have this be very small. The change in momentum is going to be very small. Therefore, we're only going to get a tiny amount of this energy actually converted. And we know we only have a tiny amount of this energy actually converted by the fact that it remains bouncing for so long. It cannot be in contact for, like, any reasonable period of time. However, what are the other things this particular mechanism requires? Unfortunately, it requires one really, really huge thing, which is this geometry here. And this geometry here, you can see, like, looking at the floor does appear flat to the disc of its size. I mean, I don't know why I drew this here, because it's no way, it's not any more to scale, but like the disc or the floor does appear fairly flat. Certainly the floor appears fatter than that disc I just drew appears round. So we don't have any geometry like this. But if we don't have any geometry like this, that mechanism I just proposed can't possibly work. Because if I just have a hole like this, and I have a bowl that's much larger, sorry, that's probably a bad example. Let's just say I have a hole which looks something like this. What we're really having is a frictional force about this point, and frictional forces about points, little dubious. Basically, the issue is we need something to push the thing down in here, and if the disc is much larger, let's say the disc is looking something like this, the best we can ever get, we're at a point. So, okay, we know we can't deal with this exactly at a point. So what I can do is I can just curve this out a little bit. This point out, and I put a little divot. But we know frictional force is parallel to the intersection between the two surfaces. But if I've got a disc like this, that parallel is pretty tiny. So this in and of itself could, in theory, be a mechanism, because here we have some conversion. This is going to push us slightly down, and this push slightly down. Sorry, I should have gone into a little bit more detail on this diagram. We give ourselves a kick this way, and there's going to be a similar kick upwards. In fact, it's not going to be a kick purely upwards. There's going to be a kick in this direction, and realistically, we actually have deflected it slightly down here. So you're going to have, so because of the fact that it's deflected slightly down, we're going to instead get this deflected what? Slightly down. That means we're slightly closer to the normal, which means we're actually getting it deflected slightly up a little bit more. But we're going to have some additional force pushing this way. So it might actually normalize. It might come out to literally, or at least a first order, it might come out to actually just precisely knocking this upwards. But knocking it upwards with increased energy, because we've added some momentum. We added a tiny amount of momentum in this direction, and we added a tiny amount of momentum to get us into this direction. But yeah, so this is one potential mechanism. However, this mechanism isn't great, and it's also not hugely realistic, because that disc is not going to be perfectly smooth. In fact, if that disc were perfectly smooth, we wouldn't use it as a grinder to begin with. And so the far better arguments we can make, why won't you delete? There we are. Is we also take into account imperfections on the thing. And at the point when you start taking out imperfections on both of the things, then you get basically, I mean, you can have this exactly the same effect. So let's imagine we've got the same thing. So I'll draw something very small. And I'm now going to draw just a tiny deviation from my perfect sphere. And now we can instantly see exactly how this effect should arise. Because now we've got a significant amount of force pushing us downwards. Effectively, what we're doing is we can instantaneously consider the axis of rotation to be about here. There will be, it won't be precisely, but we're going to have a net force. So rather than rotating precisely about its center, we're going to instead be rotating about a point which maybe looks a little bit more like here. Which means that we're going to have the rest of this approximate circle coming ramming down, and when it rams down with a ton of extra force, which it wouldn't have had, but it has because it's making contact here, it's then going to bounce up significantly more. And so, yeah, that's more or less what I would propose for the mechanism. There's one more interesting part, which is how it's, so yeah, you'll basically, it's a combination of the two effects. We both have imperfections in the floor and we have imperfections in the disc. And when the two hit, basically you get some conversion of momentum, or some frictional forces which aren't aligned parallel, and therefore which can contribute to some upwards force aside from just the normal reaction force, and that can get us the extra height. It has to be spinning really quickly for this because there are issues with this, which is like, I guess I could do the maths on it and work out, but like this thing hitting this thing, assuming that like there's some serious concerns about like how exactly the roughness interacts, but fortunately it's an ankle grinder that probably is designed to be fairly rough. I don't know too much about the details of that, but it makes sense if you're trying to strip off material that you wouldn't want it perfectly smooth. It definitely can't be perfectly smooth, whatever. I don't know the scale of the roughness, but yeah. And the interesting thing is it actually comes down to a lot more. It comes down to the average curvature of the surface. So it makes, well, not the average, the maximum curvature of the surface. So it actually makes a significantly more difference, not just the height that, say, serrations are from the surface, but actually the curvature at this point, which I find quite interesting. So yeah, that's roughly the mechanism. I think I would propose, actually, I might have to double check precisely that curvature argument. But anyway, it's something like that. But yeah, so there's the one final point, which is why does the disc come in like this direction? Because what it does is we see it come like this. It bounces itself up and then kind of almost bounces itself down. And so my first thought, just looking at this, is I don't need to worry about that. It's fine. That's fine. I actually don't have the answer to this. The previous part I had thought out, I haven't actually thought the answer to this by this point. But that's kind of looked fine. And the reason I thought it was fine is it just seems... It seems like it's conserving energy. Where it's slowing down its horizontal motion, it's bouncing higher. Does that... that seems like it works. It definitely seems like it should be allowed. The question is there a precise mechanism? I don't know. It's really the short answer. So I guess what we're looking at is the question is, does it moving this way make it more likely to bounce up higher when the disc is rotating this way? I mean, I feel somewhat intuitively that makes a little bit of sense. But it only makes as much sense if I assume we're actually going off of the pivot. I think maybe the best way you could argue that is that we know this is somewhat cutting into whatever material this is because there are sparks being given off. So maybe you can argue that the greater the relative rate of rotation, the greater, or the more it cuts into it, therefore the more time it spends there, therefore the stronger this effect is going to be. And we know this effect should decay normally over time, so that would then argue for why it goes up and then why it goes down. Is that a perfect argument? I don't think so. Can I come up with a better one? So, yeah. I mean, okay, yes, I can come up with a better one. And it's related to the fact that we actually are dealing with... Here, we're not necessarily just dealing with frictional forces, we can also be handling normal forces. And it's the normal forces which could also do this. You could actually argue normal forces a fair amount in parts of my previous argument as well. And they would also contribute to the same effect. So, okay, it makes it a lot easier when I start picturing stuff like this. Because then it makes it really obvious why we'd expect significantly more force transfer when we're going this way. Because when we go this way, this bit hooks onto there. It's already spinning quite around a lot, but now it's got some extra velocity. It hooks onto there, and that's going to rotate this entire thing down with a lot more speed. Whereas if you're doing it in the opposite direction, it's moving with. You have less force, and therefore this effect is lessened. So, I don't know. Without going through and doing the maths in detail, it seems as though this effect is actually a really interesting stochastic effect. It seems like these bounces are pretty stochastic. You can, by giving it some velocity like this, or giving it some velocity such that, okay. Yeah, when it's spinning like this, if you start pushing it this way, then you might on average give it more height, and when you go... And incidentally, that extra height will be correlated with something, with two things kind of interlocking, like I showed there. But if it is correlated, wait a second. Wait, that doesn't work. Because surely you'd expect the force to be less. If it were moving like this. If this disc were moving like that. And this hits. Like, okay, this is going much, much faster, but we're actually reducing the relative velocity. Oh, sorry, we're hitting the other side. Okay, that's fine, ignore me. So yeah, it seems as though we get a somewhat more pronounced effect when we're moving in this direction than when we're moving in this direction. And so that variation of whatever stochastic coefficient determines this could be responsible for why we're able to go up at one point, because at a certain point, because perhaps, yeah, that when we're going this way, the coefficient is actually enough that we're able to outweigh the coefficient of restitution. But when we go back, we're not. All in all, this problem really, really interests me, because it doesn't occur with perfect circles. You don't get this effect with a perfect circle on a perfect floor. However, it does something that's really, really weird, which is that we get an effect. This effect is only due to the disorder on the surface, more or less. You can also have this with an ordered surface, I should say, as well. If you had, like, I mean, me drawing it is never going to really scream order at you, but you could have this same effect with an ordered surface. However, yeah, the interesting thing, I guess, is that we're able to, in some sense, produce coherent macroscopic effect from very, very small-scale imperfections, assuming that the small-scale imperfections are matched. I find that really interesting, and something I might spend more time thinking about. But yeah, aside from actually, like, developing a proper mathematical model for this, which I'm not going to do, because I've got an exam tomorrow, yeah, that's my main analysis. Those are the rough models I would use to explain it. I think there are arguably two in there, but basically it's how you consider imperfections interacting with one another, and the fact that that changes the directions of both the normal forces and the frictional forces, and how then, what difference relative velocities then make. There are probably flaws. I think I can see arguably at least one flaw in what I've said. This was, at least with some of the normal force stuff, this was entirely ad-libbed, so hopefully I haven't said anything that's too stupid. Thank you very much for watching. I've been boiiii. I'll see you around. Bye.